Hey guys, and welcome to a new video in this algorithms and data structures tutorial. In this video we're going to talk about sorting, and we're going to talk about different sorting algorithms there are, and I'm going to show you some different kind of examples of how they work, and I'm going to show you some code examples as well, like how we can implement those sorting algorithms and use them in C++. So first of all, we need to know what an inversion is when we're talking about sorting, because we use inversions to measure how much a list or a vector or array is unsorted. So we can say that it's an ordered pair of numbers if we see here I comma j here, for which that I has to be less than j, but the index I in the array has to be bigger than the element at index j in the array as well. So an example of an inversion list down here where we have this unsorted list here, and then we can measure how much this array here is unsorted by the numbers of inversions. So we can see down here an inversion is how many different swaps we need to make until our list is sorted. So we can see down here that we have these kind of possibilities or things that we have to swap. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 inversions in this unsorted list here. So we have to do 9 operations if we're using just a standard sorting algorithm that can only remove one inversion for every operation. We're also going to talk about some other sorting algorithms that can in some cases it can remove more inversions per operation. So inversion is how much and list is unsorted. So we're going to use this to measure which kind of sorting algorithm we should use and stuff like that. But this is how we know how much our list is unsorted, and we can use this for different kind of things. So then we're going to talk about sorting, and as I just told you, the more inversions the list contains, the more unsorted it is. So sorting is used to reduce the number of inversions, and ideally we will want the inversions to be 0, because then we can swap more elements. Then we can swap more elements to get our list or our container more sorted. So when we hit inversions of 0, we have a totally sorted array. So the average number of inversions is a list of n distinct integers. Is this formula down here, which is just kind of the math for algorithms and data structures. So it's just some formula that you just plot in the number here, which is the n distinct integers, where you just plot this in and you'll get the average number of inversions in that list. If you want to know that, and in case of how many operations you need to do, and to choose which sorting algorithm you want, because if you don't have that many inversions in your list, that it could be beneficial to choose some sorting algorithm over another, and even though it has a worse time complexity, it will still be better if we had only a few inversions in our list. So if one operation can eliminate one inversion, then the sorting algorithm must have quadratic time complexity, and we're going to see some sorting algorithms that has this quadratic time complexity, where we have to run through the whole array and then sort it, and then do that for some iterations until our array is sorted. So we can also have some other sorting algorithms, let's say if more than one inversion can be removed in one operation, then it is possible to do better than quadratic, and we're going to see some sorting algorithms that actually do it better than this time complexity here. So the first sorting algorithms we're going to talk about is these a quadratic time complexity, where we have this O n squared. So it's not really that efficient time wise for algorithms, but it can be used for in some cases where we don't have that many elements, or for some of the cases where we don't have that many inversions. So the first algorithm here is the insertion sort, which is it places an unsorted element at a suitable place in each iteration. So we go through our list here, and then we just place or insert an element into that list at a suitable place. So in the end, we will end up having a sorted array. We can also have this selection sort here, which just selects the smallest element from the unsorted list in each iteration, and then it places that element at the beginning of the unsorted list. So after like a number of iterations, we just take all the like the smallest elements and then just like place that element at the beginning of the unsorted list. So we're not really going to go more in depth with these two first sorting algorithms here. If you want to go more in depth with them, like you can go check them up, or like drop a comment under if you want me to go more in depth with them. But in this video we're going to focus more about like bubble sort and some of the other sorting algorithms that has a better time complexity, and it's like more used for bigger arrays and data structures. So we can also have this bubble sort here, which is like it compares the adjacent elements and swap them if they're not in intended order. So we're just going through the whole list again here with, for example, like two follows where we just like check the two adjacent elements, and if they're not in order, we just swap those two elements and we go to the like the next element in the list and check if those two new adjacent elements are in intended order, and if they're not, we swap them, or else we just keep them as they are. So the bubble sort here is just like, as I said, but I'll just visualize it here. So in the first iteration here, like, or in the first example, like iteration here, we have these two adjacent spots here, like our elements, and then we can see that if 5 is bigger than 1, then we swap these two elements, and we can see that we did it down here, and then we go to the next spot. So we look at these two adjacent elements here, and if we need to swap those two elements because like 5 is bigger than 4, then we do that, and then we go further to the next element here, and we do the same here again for 5 and so on. And then we're done this, we're done with our first step, and we have to go through our whole list again and do our bubble sort until we have a totally sorted array. So we also have some other sorting algorithms that are like more time efficient for in some situations, and also if we're working with larger arrays or like data sets. So let's say we have, like, for example, an array that contains like 10,000 elements. Then if we have like a quadratic time complexity, that will be like 10,000 to the power of 2, like, or 10,000 squared. So that will like be a really huge number compared to if we only have this n log n time complexity here. So like these sorting algorithms that we're going to talk about now, like, they're more suitable for larger arrays. And if we're only working with like a 10, 20, 100 elements in our array, like, it doesn't really matter like what kind of sorting algorithm we're using if we're talking about like time complexity. So the first sorting algorithm here is merge sort, and it's kind of like the divide and conquer like programming as we talked about in some of the previous videos. And then we divide our list, and then we concur our list, so we get our elements ordered, and then in the end we merge all the elements again. So the merge sort here, it divides the array into two halves until we reach a stage where we try to perform merge sort on a subarray with size n. So we just like divide our array, like for each iteration we divide them in half, and then we take one more iteration and we divide the new two halves in two more halves. So we will now have 4 halves, and we keep on doing that until we have subarrays that we're trying to perform merge sort on, that only has a size 1, because then we only have one element in that array. And then we can like sort that, because then it will be in sorted order. And when we have done that, we can like merge all the elements together again, like all our subarrays together again, and then we will have a sorted array. So another approach here, or like a sorting algorithm, is the heap sort, which uses a binary tree and like, for example, a max heap. You can also use the min heap. But in this case here, we're removing the largest element from the root in our binary tree. So the root in this case here will be like the largest element when we're talking about a max heap. And then we heapify, then we remove the largest element and store it in an array. And then we heapify the trees again, so it will now be ordered, and the new largest element would now be on top, and we have like heapified or ordered all our nodes in our binary tree. And then we just keep like storing the largest element on like some other like array, and then in the end we will have a sorted array. So the last example here of a sorting algorithm is the quick sort, which is like kind of one of the most used ones, and also the standard in C++, as I'm going to show you in some code example as well, where like the sorting algorithm in C++, like the built-in in the STL library, uses quick sort as default. And quick sort is like, first of all, we choose a pivot point. So we just choose like some point in our list. It could be like the first element, the mid element, or last element in our list. And then we divide our like list into two subarrays according to whether the elements are less than or greater than the pivot. So we choose one value in our list, and then we go like through a list and check if like those elements are bigger or less than the pivot point that we chose, and if they are, we then divide it into two subarrays. So we have like one array that is less than our pivot point, and one array that is like all the elements are higher than our pivot point. And then those subarrays, then they are then sorted recursively, which we're going to see some examples on in code. So the merge sort here, if we're just going to visualize like how it works, and then we first take like the middle here, and we just like split our array into two halves, and then we again do the same here, where we split our array into two halves, and until we only have like one element in our subarray, and then we can't perform merge sort anymore, or like the merge sort anymore. And over here we do the same thing here, because we still have two elements here, and we divide it down here. So here in this row here, or at this level here, we have like all our elements stored, like all our subarrays only contains one element, and then we can sort those elements here again when we are merging our list together again. So in this case here, we can see that we're merging our subarrays together again, and it will now be this list over here. And then when we merge them together in the end here to the final list, we then do this merge here, where we then merging the list, so the elements will be ordered in the end when we have like the final sorted array down here. So the quicksort algorithm here is, again, as I told you, we first choose our pivot point, and in this case here we choose the last element of the list. So we choose 7 in this case here, and we go through the list here, or array, and then we check if the elements are less than or greater than our pivot point. And in this case here, all the numbers here to the left are less than 7, and all the elements here on the right array is greater than or equal to our pivot point. And then we do the same here again. Where we choose a new pivot point for our subarrays, and we then just do this recursively as I just told you. And then in the end, we'll just end up with our sorted array here, and we can just combine them all again. So we will now get 1, 2, 5, 6, 10, 12, 15. So then we will end up with a sorted array. We can also use this like some special case algorithm that is called a bucket sort, and in some special cases we can actually like do better than O n log n, and this is like a very special case, and you should only you can only use it if this if these different kind of special cases occur in our problem. So because then we can actually get a sorting algorithm that the time complexity is linear, which is like pretty good, but it's not really that often that we can use this special case algorithm. So if we use this bucket sort here, we need if we have like some array where we sort positive integers with a max value m, then it's possible to solve the problem by creating an m-sized array, and then the numbers, they're read from one end to the other end, from the list. So we go from the start to the end of the list, and then we're reading the value x, index x in m, and then m is incremented by 1. And then in the end, when all the numbers have been read, the array is the output in accordance with the number of occurrences in the indexes. And then after that everything is done, and we have this special case here where we want to sort the positive integers that has this is the special case up here, where we have these positive integers with a max value of m. So let's say we want to sort some values between 0 and 1. So if we have floating point numbers, then we can have like a time complexity of O of n, which is then linear and much better than like, or like kind of better than the n log n here, and definitely better than our quadratic time complexity. So just to recap before we go into code and seeing some different kind of examples of these sorting algorithms here, we just want to like recap to like get a recap and get an overview or like what we need to know before we can implement this in code. So in the start we talk about these inversions here, which just measures like how much our array or like our list or some other kind of data structure is sorted or unsorted. And then we have these different types of sorting algorithms with different time complexities, where we have this quadratic and n log n and our linear here for the special case bucket sorting. And there are different kind of approaches to like choosing the right sorting algorithm, and it really depends on your problem. For example, as I talked about, like if you have a really large array that you need to perform some sorting on, like it's better to choose like the n log n sorting algorithms here than like the quadratic here, because then it will just like end up with a really huge number and a really bad time complexity. And if you like only have like a couple of elements in your array, like it's fine to just use this quadratic sorting algorithms here, which is also like kind of like a bit easier to implement and also like work around with. Or if you have an array that is like only has a few inversions, then it's also like better to just use some of the sorting algorithms here that are quadratic time complexity compared to some of the other sorting algorithms. I just wanted to show you guys this sorting visualizer here made by Clement, another YouTuber here, where we can like have create an array here that we want to sort with these 4 different kind of sorting algorithms that we talked about in the slides here. So if we just have this array here that we want to sort with, like for example like the bubble sort, we can see that it goes through all the list, like the whole list, and then it just like swap the 2 elements if the less than or greater than, and then we just like store the elements here from the back here. So we get the largest element and the second largest element, third largest element, and so on. So we can see that if we have like a bigger array here and we want to use this bubble sort, which is like quadratic time complexity, and we want to sort it with bubble sort, we can see that is like really slow and like it takes a lot of time to sort. Like even now we don't only like sorted 4 elements in our list. So this is like not really the optimal sorting algorithm for this type of data set or like our array here, because like it's just too big and it takes too much time to sort our array in this case here. So if we just hit refresh here and try to do the same sorting with the quick sort algorithm here, we can see that this goes much faster than the bubble sort algorithm, and this will be like a more appropriate choice of sorting algorithm compared to the bubble sort if you had like this type of this size of array here. And also because like when we create a new array here, just like get randomized, and like a lot of the values are unsorted, so we have a lot of inversions. So we can also use like this heap sort and merge sort here, and we can see like we can just go in here and see like how it works. So here we just divide all of our list into smaller subarrays, and then we do this merge sort here, and then merge all the elements together in the end. So it's a pretty nice visualizer here to like see how all the like the sorting algorithms are like some of the most important sorting algorithms we have. So let's jump into the code here and see like how to implement these sorting algorithms here in C++ and see some examples of it. So we're now jumping into the Sublime text here, and I'm going to show you some different kind of examples with the sorting algorithms that I just showed you, like, or we went over in the slides. So the first one here is the bubble sort algorithm here, where we have these 2 nested for loops. So like the method behind the bubble sort here is that we look at the 2 adjacent elements in the array. So first of all, we just have this for loop here that is like running through all the adjacent elements in our array, and then we check if the element here is greater than the adjacent element in the list, and if it is, we swap those 2 elements in the list, and if they're not, we just keep them and we just go to the next adjacent element. So in this case here, we are sorting in ascending order, and if we want to like sort it in descending order, we need to change this greater than here to less than, and then we will like sort our array in descending order. So like, and then we just continue doing this until our array is swapped here with the other for loop here. So if we go down here and see like how it works, we have created this array here with some random numbers that is unsorted. So we have this unsorted array here, and we perform our bubble sort down here, and then we just print out the array here with this for loop. So if I hit Control B here, it will print out the original array before we sort it, and then we will it will print out the sorted array in ascending order with our bubble sort algorithm here. So we can see that we have sorted our numbers, or like our elements here in our array, and we get like 1, 2, 3, 4, 5, 6, 7, 8. So this like bubble sort algorithms works fine, and also with only a few number of elements in our array. So the next sorting algorithm I want to show you is the merge sort algorithm, where we like divide our list into like smaller like subarrays from the mid. So if I just go in here to the header file where I have implemented the merge sort here, we just need to like, first we have this function here that just merges two subarrays. So when we have divided all our array into like smaller subarrays until it only stores like, each subarray only stores like one element, then we need to merge all the like the two subarrays again until we will end up with our stored array. So I won't go like through the whole code here with the merge, but it's like we just take like an array here, and we take the first element, middle element, and last element, and then we just merge our two subarrays together, so we will end up with a sorted array. So the merge sort function down here is like what does like the sorting, and it calls like these recursive functions down here, where we like have this merge sort here that we call twice, and then the merge here where we merge the sorted subarrays that we have done with the merge sort here. So first of all, we just check if the first is less than the last, because the first here is the first index in the array, and the last here is the last index. So as long as we're not in the end of the array here, we just like if we don't, like, this is the same as saying that the size of our subarray is bigger than 1, because if it was equal to 1, we will then like stop this merge sort here. So then we need to find the midpoint here of our array and our subarrays when we call this recursively, and it is like the first plus the last minus this first, and then we divide it by 2 because we need to get the middle of our array. And then we call the function here again, like our recursive function merge sort here again with the array and with the first, and then the last element here in our first subarray will be the mid here, and then the first point here in our second subarray would be the first point, and the last will then be the last, because then we just divide our array on the middle, and we have a left subarray, and then we have a right subarray from that midpoint that we calculated here, and then we just do the same again until like each element in the subarrays are only 1, and then in the end here, when that is done, we then merge all our subarrays, so we'll get a sorted subarray with this function up here. So like, this is how we implement like a merge sort, and we just like divide our array into smaller subarrays, and then we sort those subarrays, and then we can merge them together again so we'll get a sorted list. So if we see that this merge sort algorithm here in code, we just do the same with the numbers here, the array up here, and we call the merge sort here. And if we Control B here again, we can see that the original array before sorting was the same as before, and then when we perform our merge sort here on our array, we will get this sorted array here in ascending order. So it works fine as with the bubble sort. So yeah, that's how we can like use merge sort in C++. So the last sorting algorithm here I'm going to show you how implement it is the quick sort algorithm here. And if you just go into the header file for the quick sort here, we need a function here to partition our array basis on the pivot element that we choose. So we also have this like quick sort function down here, where again we check if the first element is less than the highest element, and we haven't been through the whole whole list. And then we have this pivot point here that is equal to the partition of the array, and then we pass it the first index and the last index. And then our partition function here is just like it partitions the array basis on the period point. And in this case here, we just choose the period point as the last element in our array that we pass to the partition function here. And then we put all the elements that are smaller than the period point on the left, and all the elements that are greater than the period point on the right of the period. So we have a folder here to just run through all the elements in the list, and we check if the element here is less than the period, and if it is, we just increment I here because we need I in case of like we want the period point like to the right of it. And then we swap the elements here on the array at position I and j, because then we know that the element here in our array is less than our period point that we chose, and the period point that we chose is the highest element, or like the last element in our array that we pass to the partition function. And then after that, we just swap the elements here at the I plus 1 index with our period point here, because then we increment the I here if this element here is less than the period point, then we increment I here, and then it determines like which element we need to swap here with our period point up here in our array. And then we just return this index here from our partition, and then this index here is what we set equal to our pi down here, and then the pi here or our partition will be the next high here, or like the next the index, like the last index here, when we call a quick sort here again recursively, and also when we need to sort the elements on the right of the period point. So when we call these functions here again recursively, we can see that when we do this with the partition here as the highest element, then we sort the elements on the left of the period point, because this will be the highest element, or like the last element, which will be like the midpoint, and then the lowest element here. And then here again we have like the midpoint, or like all the values from the right of the period point that we chose up to the last index in our array. And then we just keep calling this recursively until we have a sorted array. So if we go down in here again to our main function, we can now perform quick sort here on the numbers array we have created up here, as in the last example as well. And if we just print this out with hitting Control B, we can see that we again sort the array in ascending order, and we sort the original array here. So we'll get these numbers out down here, and we have now sorted our array with our quicksort function. So like these are three different types of sorting algorithms that we can implement in C++. But there's also some built-in functions that you're probably going to use a lot more times. But it's always good to know what's going on behind all the built-in functions in C++, and also what it does, and why and how it does it. So if we want to use this built-in function from the STL library, I'll just go down here and we create a vector here with a bit more numbers here that we want to sort. And then we can use this built-in sort function here from the standard library or STL library in C++, and we can call this begin, which is the first element of our numbers 2 vector here. And then we will sort it until the end here with this end function here that we call on the vector as well. So if we hit Control B here, again we will now sort this vector up here, and we can see that our vector is sorted with STL function, and the STL function uses quicksort as the default sorting algorithm. And then we can see down here that it is sorting it in ascending order as default as well. And if we wanted to sort it in a descending order, we could use this R before R begin, and R in front of the end here, because then it will do it in reverse. So if we do this, it will do the sorting in reverse, and then it will sort it in descending order if you want to do that. We can also parse another parameter here, which could be a lambda function, so we can define ourselves how we want to sort our data structure or our vector. So if we want to sort in some alphabetic order, or if we had some pixel values or some other coordinates we want to sort in some way that we chose ourselves, then we can create a lambda function, and pass it to the sort function here, and then it can sort it in that way as well. So like it's pretty nice. Like we can just use the sort function here, but we also need to know like what's going on behind the scenes, and like also like how to implement other data structure sorting algorithms. So that's pretty much it for this video, guys, and we've been over like the different kind of sorting algorithms, how they work, and in what different kind of situations like some of the sorting algorithms are better than others. So thank you guys for watching this video, and remember to hit the subscribe button and bell notification on the video, and also like this video if you like the content and you want more of it in the future. I'm currently also doing this computer vision tutorial with OpenCV and an artificial intelligence tutorial. So if you're interested in one of those, I'll link to one of them up here. And you're going to go check that out if you want to, or else I'll just see you in the next video, guys. Bye for now.